Welcome to our paper towards safer and understandable driver intention prediction. Autonomous driving is not just about high performance, it's also about safety and trust. Many driver intention prediction models act like black boxes. They may predict correctly, but we don't really know why. Without interpretability, it's hard to trust these systems in safety critical environments. Interpretability, on the other hand, can help us understand model failures, improve robustness, and ultimately build safer autonomous systems. Current datasets in driver intention prediction only captures the what, like whether a car is turning left or slowing down, but not the why. Similarly, most existing models only encode spatial features from images, completely ignoring temporal and reasoning aspects. So the big challenge is how do we bridge the gap between spatiotemporal information in videos and the causal reasoning that humans use? To address this, we introduce DARX, the first multimodal explainable driving dataset. It contains multi-view video clips of 7 to 15 seconds and provides not only the maneuvers, the what, but also hierarchical textual explanations, the why. Overall, we collected 1,500 videos annotated with 32 explanations, which are 17 from ego vehicle's perspective and 15 gaze-based explanations. It also covers 7 common driving maneuvers, such as straight, right turn, right lane change, left lane change, slow down, and U-turn. This is a sample from the dataset for slow down maneuver. You can see the multimodal setup with multi-views from the front, rear, and driver-facing camera, along with gaze information. Each sample is paired with explanations that describe why the driver slowed down. In this case, the explanation corresponds to traffic ahead slows down and gazes on the traffic ahead. To improve the interpretability of intention prediction tasks, we proposed a video concept bottleneck model, or VCBM. The idea is to jointly predict maneuvers and explanations, ensuring spatio-temporal interpretability. Unlike traditional end-to-end models, VCBM builds an intermediate representation of concepts that are human understandable. First of all, we use the front view video and driver's gaze as input and perform early fusion of their features. We only use the front view video due to high correlation of gaze on front view. Further, we introduce learnable token merging block, which aggregates semantically similar spatiotemporal features across space and time. We aggregate these tokens to assign explanations to them. For example, traffic light is red can be an explanation from frame 4, 5, and 6. To cluster tokens, we use non-local blocks and instantiate clay cluster centers, which acts like a soft clustering over space and time. For token merging block, the non-local variant is chosen instead of cross-attention, since we focus on aggregation and not on transformation of tokens. Finally, we introduce localized concept bottleneck block, which takes in the cluster centers and feeds it to 17 fully connected layers. Here, each fully connected layer corresponds to one of the 17 ego vehicle explanations. Here we perform late averaging instead of conventional early averaging to classify explanations based on all the cluster centers to preserve fine-grained details. This finally provides us 17 binary outputs corresponding to explanations, which is further used to classify the maneuvers. Since interpretable inputs lead to interpretable outputs, when using a sparse MLP, the intention prediction model becomes more interpretable. We evaluate on the DARX dataset, comparing CNN-based models like I3D against transformer-based models such as Video MAE and NVIT V2. Our results show that the transformer architectures, when combined with our bottleneck design, offers much higher interpretability without sacrificing accuracy. Further, we show experiments analyzing the effect of cluster numbers and temporal shuffling. Here we show that having an optimal number of clusters around 5 to 7 gives better results. which shows adding more clusters involves noisy cluster centers and having less clusters lead to sparsity in the information. Here we show the effect of temporal shuffling. We input 16 frames to the model, which are randomly sampled from 16 equally spaced segments of the video clip. As we increase the severity, we merge the segments and sample frames accordingly to the severity number. It shows that transformer-based models exhibit better temporal coherency, since its performance reduces as we shuffle the frames. As transformer model shows better interpretability, it shows temporal understanding is important for interpretability. We analyze the component-wise contribution and it shows LTM and LCBM together increases explanation accuracy with slight drop in action classification accuracy. We also analyzed the importance of using all the tokens from the video encoder. We show that using all the aggregated tokens instead of CLS token will help in better association of explanation since it preserves fine-grained details. Here are some GradCam visualizations. For example, in the left turn scenario, the model focuses on the upcoming left turn and an obstacle, which is a parked vehicle on the left. The explanations align well with these activations, such as left turn is coming ahead and deviate to avoid obstacle. This indicates that our model's reasoning is interpretable and causally aligned. More importantly, the activations gets focused more on objects over time, just like how humans would react. Finally, we introduced multi-label TSNE visualizations to visualize explanations in the feature space. We see that explanations are disentangled into meaningful clusters in the feature space. Compared to baselines, VCBM shows better class separability and alignment between maneuvers and explanations. For example, the explanation vehicle at intersection and traffic light is green can be found across multiple maneuvers, so it is supposed to be at the center. To conclude, we present DARDX, a new dataset with explanations for driver intentions, and VCBM, a model that makes predictions more interpretable. Together, they push towards safer and more trustworthy autonomous systems.